Welcome to this video on chi-square testing procedures. This video is going to touch on the goodness of fit test. And there are two other tests, the chi-square test for independence and the chi-square test for homogeneity, but that will be in the next video. All right, so what does this test do? It looks to see if your distribution that you got in your sample matches your hypothesized distribution. We're going to do an activity in class with M&Ms where you're going to see if the sample of M&Ms you get, if the color distribution matches what the candy company states that they put into their bags of M&Ms as their color distribution. In this video, we're going to do an example with cell phone crash data and see if that matches with our hypothesis. So we have a study that has 699 cell phones related collisions, and we have it classified by week. So we want to see, does this data occur equally per day, and does this data support that? So we are thinking it doesn't matter what day of the week it is, cell phone crashes happen equally. We got this sample, we want to compare it and see if they do indeed have no day has no impact on the number of collisions. Now, the null and alternative hypothesis for this kind of test is a little bit different. The easiest is to write it into words. You could do symbols, but as you can see here, it gets a little tedious because for this example, there's 7 categories, one for each day of the week, and we want them all the proportions of the accidents to be equal to 1/7 divided among the days. And then the alternative is that at least one is different, but you could write it in words, which is just that the motor vehicle accidents are equally likely each day of the week, and the alternative is that at least one day varies. Okay, so first step when you're doing a chi-squared is to get your observed counts and your expected counts. This one, the expected counts are fairly easy. You just take the 699, divide by 7, that's how many occur each day. It is okay for your expected to be decimals. Your observed cannot be because you can't have half a person. And if this down here, the capital X, it's usually more of a cursive EX, is your chi-squared statistic, like your T and your Z statistic. And if you look at the equation to calculate your chi-squared, it's a little similar to the Z and T in that in the Z or T test, you take your sample, you minus the population or your expected value, and then you divide by your standard deviation. So there's a little bit of that going on here. We got our observed minus expected, and then over the expected, which is kind of like the spread of your data a little bit, but not really. But it has a familiar look at least. Notice it's chi-squared, and we do have a squared. This formula is given on your formula sheet, so you don't have to have it memorized, but after you do it a couple times, you'll have it memorized. All right, conditions. Conditions for the chi-square goodness of fit are actually pretty easy. You just have to make sure all your expected counts, and that's the key. It's not your observed counts, it's your expected counts, are at least 1, and no more than 20% of the expected counts are less than 5. So depending, like if you had 10 different categories, then only 2 could be less than 5 out of the 10. Oh, one other thing is on the expected counts, it's not always that they're all equal. You could have, like you expect when we do the M&Ms, we expect more browns than blues, so they don't have to be all equal. It's just in this case they are. All right. And that's the only condition, which is nice. All right, we also have degrees of freedom in this test, just like in the t-test. For this test, it's the number of categories minus 1 is your degrees of freedom. And the chi-square has its own distribution. We're not using a normal curve on this. The chi-square is a right-skewed distribution, and that's because your chi-squared value can never be negative because of this, how it's created. So you're never going to have a negative chi-square value. It looks like this. We're still figuring out, area under a curve, probabilities, but the shape of the curve is different. All right, so here we have our values, and we're going to be putting these into our calculator in a minute, into our lists. And it's good I usually just do this list 1 and list 2 in my calculator. And your calculator on the output will give you what are called the contributions, and it will, I think it abbreviates it to this. We'll see if I remember correctly when we go to the calculator. It'll give you that the observed minus expected squared over expected part for each term. And so you can see which one has the biggest contribution to the chi-squared value. And as the chi-squared value gets up higher in value, obviously your p-value is going to get smaller and you'll be more likely to reject the null. But it can be useful to see which term contributed most to the chi-square value, because then you might want to go back and look at, like in this case, that day specifically, what's going on in that day, why is that having more collisions? All right. So if you want, you can go through by hand and just calculate these just to make sure that you got the mechanics down, because you would have to show this in a free response if this were in an AP question. Usually they only give you a few terms in your chi-square value if they're going to have you do it out. So our chi-square value is 208. Now this is not like a z and t-score where we're 208 standard deviations above the mean. That's not what this value means. So don't think, oh, well, this is going to be, our p-value is going to be 0. Not necessarily. It depends on how many categories you have, because as you can think, as you get more categories, generally your chi-square value goes up because you're adding more things into your chi-square value. All right, so let's do the calculator. All right, so here we have, you go to our list to edit, put the data in the list. And I just need to see what are the numbers. 99.875. Okay, thought it was 57. All right, so you can type in these values. I forgot to type in the expected values. Oops. All right, so pause here if you still need to type in some values. I'm going to now show you where to get your test. All right, so we are going to, like just before, go to stat test, and we go down to chi-squared. So this is your chi-square goodness of fit. The next video is going to go over the chi-squared test. And one of the ways you can tell, I'm going to just click on this so you can see why you would know right away you're in the wrong place. This has this notation, and if you've never seen it, the observed and expected, that notation is for matrices, which tells you right away you're in the wrong place because you put your data into lists. So we want chi-square goodness of fit test, and our observeds in list 1, our expected in list 2. We had 7 categories, so our degrees of freedom is 7 minus 1 or 6. And our calculated chi-square value is 208. Our p-value is very small, even though it doesn't totally mean the same as standard deviation. I mean z-score, like how many standard deviations above the mean you are. but we still get, essentially 0. And if you haven't touched anything on your calculator, you can scroll through and see which term gave you the biggest contribution to your chi-square value. So far, oh, it's this last one. The first and the last one, which I think are the weekends, yes. And as you could probably have thought, those two are the ones with the fewest accidents. And then you can probably think why, less people on the roads commuting. But then you could go back and look at the ones that provided the biggest contribution and then do more analysis into what's causing those. All right, so that is the end of goodness of fit. We'll do some more in class and we'll do some more practice. I will see you in the next video.